So here's a positive feedback circuit that we're going to analyze, and then we will explain the application. So I'm not going to talk about applications first. We'll get to that at the end. So this is called the Schmitt trigger. And it's an op-amp with positive feedback connected like this. So it looks a lot like our amplifiers. We have our voltage input into the inverting input, and the non-inverting input is the one with feedback. So I'm going to draw this. It turns out this is, I think, the same as the non-inverting amplifier in terms of what the connections look like, just the plus and minus are switched. I'm going to draw it just slightly differently than we drew that, though. So here we have two resistors, R1 and R2, and this is our output voltage. And we'll call this voltage, we'll call that point A, so that's like voltage, VA, voltage at point A for reference. Okay, so let's, just for the sake of numbers, let's say that R1 is equal to 9 times R2. Then the voltage divider here we get means that VA, you can check this yourself, VA is equal to exactly 1/10 of V out. So whatever our output voltage is, our voltage at point A is 1/10 of that. That's the same as the voltage across R2, right? That is, the voltage across this is the same as the voltage at point A. Okay, so let's say that our output voltage is minus 15 volts. So that is our maximally negative voltage, I guess our minimum voltage. And if that's the case, then our voltage at point A is equal to minus 1.5 volts. Okay. So if Vin is at, so given this starting circumstance, let's also say that Vin is at 0 volts. Is our system happy? Well, right now, so Vin is V minus, and VA is V plus. So V minus is greater than V plus, and it turns out that that difference between those is 1.5 volts. So if our, I guess delta V should be minus 1.5 volts. So if the open loop gain of our op-amp is big, 10 to the something, that means that this voltage difference at the inputs is going to be multiplied by some big number to give us the output voltage, and that is going to be big enough that this is going to be at that maximally negative value. So in other words, because this delta V is negative, because V minus is bigger than V plus, V out is going to be happy at minus 15 volts. Because this small difference, if we're going strictly by the numbers, minus 1.5 times 10 to the fifth says there should be a difference, it says our output should be minus 150,000 volts or something like that, but we're limited, we're limited to minus 15, so it'll just be minus 15. So anyway, output is happy is the way we will say that. Everything is consistent with this picture. Okay, so if we change our input value now, I'm gonna erase this. So if we change our input value, so let's say we change it from 0 volts to 5 volts or something like that. So if Vin is 5 volts, that is now equal to V minus. If V plus is still minus 1.5, our system is still happy. Our output is still happy to be at minus 15 volts because V minus is bigger than V plus. In fact, that will be true for any value. Our output is going to stay erase this. As long as the input stays above minus 1.5 volts, since that is where this is. And of course, maybe it's not 1.5, maybe it's, 1.50005 or something like that. But, stays above almost exactly minus 1.5 volts. So if our output goes, if our input goes below minus 1.5, let's just kind of step through what happens. So let's say that now Vin is equal to minus 1.51 or something like that. So now, and this is equal to V minus, remember. So now V plus is greater than V minus, and that 0.01 volt difference is going to be what we get at the output multiplied by our gain. So our output is now, 0.01 times 10 to the fifth, which is, 1,000 volts, but really that just means we will be at plus 15 volts. So as soon as this goes down as low as minus 1.5 anything, 1.51, our output is going to flip from negative to positive. So when it does that, we'll erase this. So when it does this, the output changes. That means that VA also changes. VA changes from minus 1.5 to plus 1.5. So if this is plus 15, this is plus 1.5. And now that is a different threshold that we have to contend with when looking at the relationship between our input and our output. So in other words, once this happens, our output is going to stay there as long as our output is below plus 1.5. So this is kind of funny behavior, and it's easiest to see what's going on if we draw a little graph, I think. So if we graph our output as a function of our input, and our output can only be two values, right? It has to be either plus 15 or minus 15. We saw if our output, if our output starts at minus 15 down here, it is going to be happy for any value of our input. Let's just actually walk through these in the same order we went. So we started out with V out at minus 15 and V in at 0. So V out's at minus 15, V in is at 0. So we started off here. We said this state was stable for a whole bunch of different input voltages, and in particular, it was good for any input voltage bigger than minus 1.5. So if this is minus 1.5, all of these states, this is minus 15 volts on the output, all of these states, our system is happy. If we go below minus 1.5 though, all of a sudden we switch. So if we go too low this way, we switch up to this plus 15 volt output, which is stable for any value of the input up to plus 1.5. At which point, if we go above that, we switch back to minus 15. So we have these two stable states and these two transitions that can happen between them at these two different voltages. Okay, so there's, as simple as a graph as this is, there's a million things to say about it. I won't be able to say them all, but here are the important points. When we are at V equals 0, or sorry, V in equals 0, so on this line somewhere, there are actually two stable states that our system has. We could be either at plus 15 or minus 15, depending on what has been happening previously in our circuit. And that's true for other values near 0 too. In fact, it's true for every voltage between minus 1.5 and plus 1.5. It's only when we go above that that we know we're in this state down here, or if we go, below minus 1.5, we know we're in that state up there. Okay, so this is the first circuit we have seen that has a memory. And I mean that in the figurative sense, but also this is how the first ideas of digital memory and storing information electronically really got started. So the circuit has memory, it has two stable states, and it will stay, in that stable state until you give it a signal to push it out of it. Because there's two stable states, this is sometimes called a bistable circuit, and we'll see more examples of bistable circuits later on. All right. Cool, so the Schmitt trigger. Now it has memory. This is not how we actually store information on computers though. This is not terribly useful for that. There are much, much better ways of doing this, but this is a useful circuit, and here is why. I want to compare this to our I want to compare this circuit to our comparator circuit, which the comparator circuit we looked at before was like this. So this was maybe our first op-amp circuit, where we have an input, we have an output, and this op-amp is giving us an output that depends on the input in a very simple way, right? If the input was greater than 0, then V out was equal to minus 15. If V in was less than 0, then V out was equal to plus 15. I don't remember if this is the exact comparator we analyzed before, but these are the numbers for this comparator with V in on the inverting input, right? If this is more positive than 0, if the inverting input is more positive than the inverting input, which is 0, the output is going to be negative 15, and that's what we see here. Okay, so this comparator, we said, well, this could be a useful circuit if you had a signal you were sending to it and you want some output that all it cares about is whether it's above some threshold value or below some threshold value. Maybe there's a temperature sensor and you want to turn something on when your temperature sensor voltage goes above some particular set point value or something like that. There are lots of reasons you might want a circuit like this. One problem with circuits like this is that this input voltage is not perfectly, precisely clean. Like, let's say we have some input signal that looks like a sine wave, I don't know. And we want to turn on our comparator for the positive parts and turn it off for the negative parts. So like this comparator, ideally for this graph, here V in is positive, so V out is negative for all this, and then when it crosses 0 again, it's positive for all this, or something like that. This is like roughly what this circuit would do. But like I just said, our input voltage is really not a perfect sine wave. No matter how clean of a signal you're putting in, there's always going to be some little noise there. So if you zoom in on this piece right here, this sine wave line doesn't really look perfectly flat. It looks like that. And the problem with this is we're comparing this voltage that is not perfectly straight line. It's going up and down a little bit. We're comparing that to 0. I'm going to draw this even bigger. There's no reason it has to be zigzag. That's just, what I've drawn. So if this is the 0 we're comparing it to, the real output that our perfect comparator would give us for this noisy signal would look like this. Here we're above 0, so this is going to be minus 15. Here we dip below 0, so now it goes to positive 15. Here it goes above 0 again, so we're down to minus 15. Here it goes below 0 again, so now we're down to minus 15, or up to positive 15. And so instead of our output being this nice perfect square wave, our output is really flipping back and forth each time our input crosses 0. This could be a big problem, especially if our job is to count how many times this crosses 0. That turns out to be a useful thing to do in lots of circuits. So here, where our black line has gone through 0 once because of this noise, we actually counted, 3 times or something like that. So this would be a big problem if you were trying to precisely count how many times this oscillated or something like that. But there's a solution, and that solution is the Schmitt trigger. So the idea with the Schmitt trigger is once you cross this threshold, that threshold moves. It gets further from where you are, and it gets harder to change your state because of this positive feedback. The positive feedback is tending to keep the circuit at the same output it is at. So in other words, here I'm going to try to imagine that we're this that we're this black input signal on here. So our voltage is decreasing, right? We're starting at some positive input, and I'm zigzagging back and forth because there's a little bit of noise, right? Zigzagging back and forth, and nothing's going to happen until we get to this threshold. And as soon as we get there, now we're up at this plus 15 state. We're still oscillating back and forth, but now we're so much further. In order to flip it back and forth again, I would have to all of a sudden have a voltage all the way up here. So even if my voltage is varying over, I don't know, what is this on the graph, like 1 volt, once this switch happens, that 1 volt of variation is nowhere near enough to flip it back the other direction. And so the output of my Schmitt trigger is only going to flip once in this down process, whereas the simple comparator flipped 3 times during this process. So this might seem esoteric. It turns out this is super useful. It is useful for us in the lab. We're not going to be able to do a lab that uses this, I don't think. But whenever you have mechanical switches, so like switches that you press a button and the metal closes or opens, you can have what's called switch bounce. So the metal surfaces bouncing or rubbing over each other can create noise that looks like this. So if you're turning a switch on and off and having circuits measure that, you might end up inadvertently, each time you switch it, switching it on and off 5 times or 100 times or something like that. So a Schmitt trigger circuit can make it so that switching event electronically only happens once. So even if your input is shaking around a whole bunch of times, the switching of the output only happens once, and that can solve a lot of problems in circuits. So broadly, this is called debouncing. Switch bounce is the thing that causes this, and so debouncing is like removing the switch bounce. Anyway, not as esoteric as it seems. It shows up in a lot of different places. But this is one of several applications of positive feedback in op amps or op amp type circuits.